So thank you very much to the organizer for inviting me to this meeting. I am really thankful to the organizer. Okay, so I also thank I thank especially Nikolai for sort of bearing all my requests about date change and schedule change, and finally to Mahinder for kindly agreed to swipe his talk with that of mine because I have to travel somewhere tomorrow around the same time, and I will not be able to give the talk if it was held tomorrow. So thanks Nikolai, thanks Mahinder, and thanks all the organizers, all the friends from Russia and elsewhere for organizing this wonderful conference and for giving me the opportunity to speak. Now, my talk here, as Prabhakar mentioned, that it is about linking of group elements. So this is a conference on knot theory, where linking of circles or the linking of knots played an important role. So I just give a sort of statutory warning that the concept that I will now describe, I do not know whether that has any connection with the linking of knots or not, but it is a nice geometric definition, but it is valid for any abstract group. Now, to motivate my definition, first I will define what do I mean by reversibility in group. So let G be a group. You can take any group. An element G is called reversible or real if it is conjugate to its inverse. If G is conjugate to G inverse in G, that is, there exists H in G such that G inverse is HG H inverse. So this is the, there are two ways one studies reversible elements in a group. One approach is using algebraic viewpoint. So these elements, so the motivation to study such elements comes from both classical geometry and classical group theory or representation theory, whatever group representation theory. All right. So the point is this concept. Okay. So this concept is intimately related to another notion, which is called strong reversibility in group. So an element G in G is called strongly real or strongly reversible if G can be expressed as I1, I2, where I1, I2 in G and I1 square is 1 equal to I2 square. That means if one can express a group element as a product of two involutions, then it is called strongly reversible or strongly real. Now, in classical geometry, such elements are called bireflectional. So in classical geometry, it is a common problem that you take any geometric automorphism, one wants to decompose that as a product of reflections, which are special kind of involution, and it is a common problem to write them as a product of minimum number of involution. And when the minimum number of 2, they are called strongly reversible or strongly real. Now here is a quick observation. Strongly reversible elements are reversible because if G equal to I1, I2, then G inverse is I1, I2, I1, I1. And since I1 square is, so note I1 square is I1, and this is same as, okay. So G inverse is, yeah, so this is G, okay. Yes, okay. So automatically it follows that strongly reversible elements are reversible, but the converse is not always true. But the converse is not true. If time permits, we will give you example, but it's not difficult to find example. Okay, so in the literature, it's in the literature, for infinite groups, a central problem is to find groups where the converse holds. Okay, or find not groups, I mean, I would say groups and group elements. Okay, groups and group elements where the converse holds. All right. So this is a central problem in the literature, but normally, I mean, it's a general problem in my opinion, and I think answer is not very well known in most of the group. Okay, I see in my slide, that's better. Okay, so general problem. Okay, so classify reversible and strongly reversible elements in your favorite group G. Now, this problem, I think, has been studied mostly by finite group theorists, where considerable progress has been obtained. So in finite group theory, the problem is better understood. Okay, so there are finite groups where every element is real, and there are finite groups where every element is also strongly real. I mean, the literature has full of research papers in this direction, but I will not mention much. But one can, for example, look at paper by T.F. Zaliski or Vodovin and Galt, okay, and maybe Binroot, okay, and yeah, and many more people where this problem has been studied. Uh, yeah, but in infinite groups, for infinite groups, complete classification of such elements are known only for a very few families. I mean, for most of the infinite group, I mean, and mostly for linear groups, it is known, all right. But for major number of infinite group that we encounter, it is not very well known. Okay, and so it's an interesting problem to study this problem. Now, as I mentioned at the beginning, that the motivation come from finite group theory. So now you see, I mean, I have at the beginning I have said that reversible elements are also called real. Now, why they are called real? That motivation comes from this finite group theory. So I will just give you the motivation for calling them real, and also the motivation for calling them reversible. So let G be a, so let's call it motivation. Okay. Motivation. So let G be a finite group. Okay. Then it is well known that the number of complex irreducible characters of G equal to the number of conjugacy classes of G. Now, in 1906, Frobenius and Su, they proved that the number of real irreducible characters of G is equal to the number of real conjugacy classes. That means conjugacy classes that contains both G and G inverse. Okay, so this theorem tells you the importance of finding the real conjugacy classes, or the number of real elements in a finite group G. And that's why when one looks from algebraic viewpoint, they call it real. On the other hand, if you look at just the action, say you take the upper of space and just look at the action of the translation on the real line, okay, then you can easily see that this alpha and z goes to z minus 1, alpha inverse, they are not conjugate to each other. All right. So in classical geometry, when one classify the, for example, the rigid motions, it's an interesting problem to find out Euclidean isometries which are product of two involution. In particular, it is interesting to find out which elements are conjugate to their inverse. Okay, So for example, if you take the rotation, also if you take the rotation in an angle theta, say cos theta minus sin theta, cos theta, in matrix notation, if you call it A, then A is conjugate to A inverse in the full group of, uh, a full orthogonal group, but you cannot conjugate them in SO2. Now, when you take A, it's a rotation in an angle theta, and A inverse is, you can think of it as its reverse, like it's a rotation in an angle minus theta, right? So that gives you the notion of reversibility in classical geometries, but mathematically they are the same. Essentially, we are trying to understand when an element is conjugate to its inverse. Okay, so the problem of reversibility has also, so the problem, the concept of reversibility occur in mathematics from different viewpoints. Now here is a exposition. So refer to. So there is a book which is called Reversibility in Dynamics and Group Theory by Anthony O'Farrell and Ian Short. It's a London Mathematical Society lecture note series. Okay, so this book gives you a nice overview of this problem in group theory and geometry and also partly dynamics, and it's more or less a good survey to understand more about this problem. But in spite of many work, a complete and concrete classification of such elements are known only for a very few families of infinite groups. Okay, so that's what we wanted to study, that we have certain groups in mind, and we have studied reversibility and strong reversibility for such groups. Now, one such group comes from classical geometry, like groups of Hermitian spaces, or the isometric group of the hyperbolic space. Okay, so now in this talk, what I will I have the main object of my talk I have not defined yet, so that's what I will do now. So linking. Okay, so before that, linking. Okay, so linking pairs. Okay. So linked pairs in a group. So this is again a very general definition that I will make. Okay, so let G be a group. Okay, assume that assume that G has, okay, let's G be a group assume that G is strongly reversible. That is, every element is a product of two involutions in G. You can also take some finite extension of G and do it there, but let's, for simplicity, assume it's a product of two involutions in G. Then a pair G1, G2 in G is called linked if there exist involutions I1, I2, I3 in G such that G1 equal to I1, I2, G2 equal to I2, I3. So that means essentially you take two different element from G. If there is the involution that is common in their involution decomposition, then this pair is called a linked pair. Now again a problem, potential problem. Classify linked pairs in a group G. Now, how does that problem occur in literature? So this is a problem I do not think in finite group theory or in any other branches of group theory anyone has studied this problem. It is, I mean, the only source where I have seen this problem comes from hyperbolic geometry. So let me tell you the motivation from where the motivation comes from. So it's a classical theorem by Musket. Okay, you can find this theorem in Musket's book on Kleinian groups. Okay, so let G be PSL 2R or PSL 2C. That means G is the isometric group, the identity component, the orientation preserving isometric group of hyperbolic 2 space or hyperbolic 3 space. Okay, so HK is the hyperbolic K space. That is the same as you can take DK equipped with the constant negative curvature matrix. Okay, I mean there are other description also. I mean more linear algebraic description, but let me not talk about that at the moment. So you start with G to be PSL2R or PSL2C. Let A be in G, generate a non-elementary subgroup of G. Then there exists involutions I1, I2, I3 in the full group of isometries such that A equal to I1, I2, B equal to I2, I3. Okay. When G equal to PSL 2C, one can choose I1, I2, I3 from PSL 2C. So this gives you a nice characterization of linked pair in low dimensional hyperbolic geometry. And this is the motivation for, I mean, this is a motivation for me, at least, for looking into these elements. Now, this is this is the work of Musket, and not long back, around 2012. So Basmajian and Musket, they discussed generalization of the above result in classical space forms. In particular, for isometric group of Hn. But I don't think that a complete classification is there in their work. So it appears at the transaction of, they have this paper in Transaction of American Math Society, where they have discussed generalization of this work for classical space form that includes the isometric group of the Euclidean space, the spherical geometry, which is the orthogonal group, and of course hyperbolic spaces. All right, so they generalized this problem. They have discussed at least generalization. And now it is not that Basmajian and Musket have thought of generalizing this theorem by Musket for other geometric spaces. Now, in complex hyperbolic geometry, this problem has also been investigated. So let me mention briefly about that. So generalized, I mean, there have been attempts. So there have been attempts to generalized Musket's theorem in the complex hyperbolic geometry, where the group is SU 2,1. Okay, so now there are results. So for example, Pierre Will obtained generalization for loxodromic pairs, and Poppert and Will, alphabetical right anyway. So Poppert and Will, they did it for arbitrary isometries. Okay. Yeah. So classified link pairs for arbitrary pairs. Now, in complex hyperbolic geometry, they have discussed two kinds of linked pair. One they call as R decomposable, and the other they call C decomposable. So R decomposable means you start with an element here. So G in SU 2,1, then one try to find out G1, G2 actually. Yeah. So then it is known that every element is a product of two anti-holomorphic involution, right? So R decomposable means linked by anti-holomorphic involution. So let's so linked by anti-holomorphic involution, and C decomposable means linked by holomorphic involutions. Now, these C decomposable pairs have also been classified by three authors. Those are Chinese authors. I have forgot their name. I think it's Jiang and yeah, it's let me title the name. Uh, uh, so Jiang and Z. I mean, yeah. So also C. Okay. So also for C decomposability, it is Rain, Z, and Jiang. I mean, they have also worked out all C decomposable pairs in PU2,1. All right. Yeah. So that's a scenario for complex hyperbolic setup. Now I will come to the to my interest. So now the question: what about linking for what about linking for isometries of the two-dimensional quaternionic hyperbolic space? Okay, because that will sort of complete Muskit's result in two-dimensional hyperbolic geometries. When there is one more geometry, which is the Cayley hyperbolic plane, but that there is something that I will not discuss, because that's there the isometric group is not linear, and it's non-linear kind of it's an exceptional Lie group. Yeah, so that is slightly more tricky, and I would not mention much about that case because I have no idea what is the scenario there. But what about isometric group of the quaternionic hyperbolic space? So in this case, G is SP 2,1. So now maybe this is the time that I will briefly describe what do I mean by quaternionic or complex hyperbolic space and their isometric group. So let P is you take F3, where you can take F to be R complex of the quaternion. All right, then equip. It's a very much linear algebraic definition of the hyperbolic spaces, which I am giving. Equip V with Hermitian form ZW, which is minus Z1 W1 bar plus Z2 W2 bar plus Z3 W, maybe Z1 bar W1. Let's take that. Okay. Z2 bar, Z3 bar W3. Okay. So this is signature 2,1 Hermitian form. Now, this Hermitian form decomposes the whole space B into three disjoint subsets. So this is the subset B in B, such that this is greater than 0. This is the subset B in B, such that the inner product or the Hermitian form is less than 0. and this is the subspace B in B, such that their Hermitian form is 0. So this is the decomposition of B into 3 subspaces. Now for me, I mean, you take the projection of B to the projective space. Okay. The hyperbolic space is defined to be the image of the projection of V minus. Okay, so now you can easily see that if I take ZZ, then this is minus mod Z1 square plus mod Z2 square plus mod Z3 square. Now this is less than 0 on H2F. So this coordinate has to be non-zero. So now you normalize to projective coordinates. This implies minus 1 plus Z2 by Z1 square plus Z3 by Z1 square less than 0. This is same as, you know, say alpha 1 square plus alpha 2 square 1. Alpha 2 square is less than 1. Okay, where alpha 1 belongs to F2. Okay, so this identifies the hyperbolic space with a ball inside F2. Okay, and that's the usual notion. And accordingly, this also shows that the boundary of the hyperbolic space is this thing, which is same as alpha in F2, such that alpha 1 square plus maybe mod alpha 1 square. Okay, sorry, mod alpha 1 square plus mod alpha 2 square equal to 1. So this is the usual way we think about hyperbolic spaces. Now, when F is real, this is the usual hyperbolic disk. When F is complex number, it is the two-dimensional hyperbolic space. And when F is quaternion, it is the two-dimensional quaternionic hyperbolic space. All right. And the isometry group of H2F consists of all elements in GL, in this case 3F, such that A bar transpose JA equal to J, where J is the matrix, the diagonal matrix that represents this Hermitian form. Okay, so when F is quaternion, we denote the isometric group by, I mean, yeah, sp2, 1. So this group, I mean, isometric group is given by, okay, let's see, let's call it U2, 1. Okay, so when this is H, then U2, 1 H is denoted by sp2, 1, and the isometry group of the quaternionic hyperbolic space is simply sp2, 1 modulo plus minus identity, which we denote by psp2, 1. Okay, so this is the isometric group that we want to work, and our problem: understand linked loxodromic pairs in PSP 2,1. Now, does it make sense to ask it for PSP 2,1? The answer is yes. So with Sushil Bhunia and I think in 2020, we proved that every element in fact in PSPn, 1 is a product of two involution. So every element in PSPn, 1 is strongly reversible. So that means the problem is very much natural to ask for this group. Now, I mean, for arbitrary dimension, I expect it to be more complicated, but at least we can ask it for n equal to 2, and that's what I want to discuss now. Okay, so we want to understand the linked loxodromic pairs in PSP 2, 1, but before that, I need to define what do I mean by loxodromic pair. Okay, so fact, you take any G in PSP 2, 1, then G, okay, then not fact, let's take it as a definition. Let G, then G is called elliptic if it fixes a point on the quaternionic hyperbolic disk. G is parabolic if G is non-elliptic and G has exactly one fixed point on the boundary, and G is hyperbolic if G is non-elliptic and G has exactly two fixed points on the boundary. Now by G loxodromic, okay, so it's a fact that G in SP2, 1 implies G is either of the above three types. So G cannot
Krishnendu, is there any issue? Or your screen got stuck? Seems some issue. Am I audible, Nicola?
Yeah, hello. Hello.
Yeah, hi, Krishnendu. Yeah,
Yeah, so I was disconnected actually.
yes, yes, yes.
Yeah,
You
yeah,
can,
yeah. Let me join back again.
yeah, please.
Yeah.
Recording in progress.
You have 5 minutes, you can wind up.
Yeah, yeah.
You can wind up in 5 minutes.
Yeah, yeah, yeah. Wait a minute. So let me share my screen. Yeah, so suddenly I don't know where I was, but the point is, yeah, so every isometry, every quaternionic hyperbolic isometry is either elliptic, parabolic, or hyperbolic. I think I was there and up there. And if it is hyperbolic, then it is up to conjugacy of this form. Okay. Now, an element G in PSP 2,1 is called, or we can even take SP 2,1, is called loxodromic if G has no real eigenvalue class. That means all these numbers are purely complex number. I mean, in that case, we call it a loxodromic element. Now, in a joint work with Sagar Kalane, we have classified linked loxodromic pairs. In PSP 2,1. Now, I mean, how do we do that? That's slightly, I mean, it will take some more time. So I will not say that, but what I will do here, that I will write down the statement. Okay, and that should, I will not prove it. I just write down the statement here. Okay, this is still an ongoing work. So, but this result, I think we have already obtained. So I'm noting it down. So let G1, G2 be pairs of loxodromic elements in PSP 2,1 without a common fixed points. Then G1 and G2 are linked if and only if there exists involutions I1 in PSP 2,1 that permutes the fixed points of G1 and G2 and acts as a right turn on the respective eigenspheres of G1 and G2. So what happened in matrices over quaternions, they do not have any well-defined concept of eigenvalue, because suppose you take a eigenvalue like this, then GVQ will be Q inverse lambda Q. So that means this will be the eigenvector corresponding to this eigenvalue. Since Q, lambda, Q, these are all quaternions, they don't commute with each other, right? So in quaternionic linear algebra, the eigenvalues appear in similarity classes. And one can identify the eigenspace, one can project the eigenspace to a sphere where each point on the sphere represents a point in the similarity class of eigenvalues. So each point on the sphere represents a vector corresponding to a similarity class in the eigenvalue class. Okay, so that means you have the similarity class of eigenvalues. So corresponding to each class, you have associated one vector, and that gives you the eigensphere of the eigenvalues. So now this result states that if you have an involution I1 such that this happens, then G1 and G2 are linked. But yeah, so there are numerical conditions when such a I1 exists. So there is a concept of angular invariant. So we think that when the angular invariants are equal, that will guarantee linking. That will guarantee existence of such involution I1. So we are trying to work that out and associated to this geometric version of the theorem with some numerical invariance. Yeah, so it's still an ongoing work, and we hope that we will be able to understand some more in the coming days. Thank you.
Thank you, Krishnendu. Any quick question from the audience? If there are no questions,